So now it is NoSQL time. NoSQL stands for not only SQL. It's really open-ended. As the name implies, we do not have standard query language for NoSQL databases. But really a better name for these type of databases is non-relational, because that's really it. These databases do not have relations the same way that relational SQL databases do. And so we can't really use standard query language to join tables and to query them and do kind of those complex operations. But non-relational databases come in all types of shapes and sizes. There's a lot of variations. SQL databases were originally used for a long time, for literally decades, but recently in the 2010s, NoSQL databases have become popular to kind of get past some of the limitations of SQL databases. But that doesn't mean NoSQL is, superior. There are trade-offs between these types of databases, relational versus non-relational. And by far the biggest limitation that NoSQL databases can get over is scale. That's usually the biggest problem that NoSQL databases are trying to solve. They are trying to scale up more than regular SQL databases can. We'll talk a bit more about that later on, but for now, let's talk about a few variations of NoSQL databases. The first and most simple one is a key value store, and I guess you could argue that this isn't necessarily a database because most of these are in-memory stores. They don't use disk. Like Redis, we've kind of already talked about that throughout the course. There's also Memcached and etcd. These are some popular key value stores, and they do work pretty much just like a hash map. They take some key value, like, somebody's ID, and then map it to some object, which is going to be flat in nature. Like, they can have some fields, but that's pretty much it. We don't have relations between these, key value things. There's no foreign key constraints. There's nothing like that. I mean, these IDs themselves, these key values do have to be unique. You can think of that as like the primary key, but other than that, it's pretty basic. The benefit is that if you need just a very simple scenario, and you need to read and write a lot of data very quickly, Redis and Memcache, because they use RAM, they do not use disk, they are very quick. So you can see that that's kind of the trade-off we make when we use key value stores versus using a regular SQL database. Usually key value stores are used together with like a primary database. The key value store would typically just be used for the cache, sort of what we already talked about a few lessons ago. Next, we have document stores or document DBs. These are sort of a step up from key value stores. It's basically that we have a collection of documents. So with SQL, we had a bunch of tables and rows. With document databases, it's more that we have a bunch of collections, which are basically a container for documents, and this would be an instance of a document. A document, really, the simplest way to think about it is it's just a JSON object typically. Like, it's a bunch of key value pairs that could be nested. So a document itself is going to have some type of primary key that is identifying it, and then from that primary key, we get an object. But this object is not flat in nature. You can see it's nested. Like, we have a couple fields out here, like it's just like a JSON object. We have a field out here, which is its own object. And then that object itself, which has a list of values, and that list contains some more objects. And then finally, we get to the individual key value pairs. ID is 1, name is John Doe, and a bunch more stuff, right? The benefit of this is that it's a lot more flexible than a regular SQL database, where we actually have to define a schema for every row in a table. With collections and documents, there is no such thing. We do not have a schema for the document. We can literally just keep going. We can, mix and match types. We can do anything. We can keep adding fields that don't exist right now. We can remove fields. There's really no constraints generally. And this flexibility is why you would use a document store. Well, at least that's one of the reasons. The other reason for using pretty much any NoSQL database is scale, and that's definitely the case with document databases as well. The most popular open source document-based database is definitely MongoDB. You've almost certainly heard of it, even if you haven't used it. There's also wide column databases. We won't discuss them super in depth because they can get pretty complicated, but at a high level, these types of databases can handle massive scale, but they're typically oriented for a lot of writes. Like if you have a lot of writes that you're storing in a database, like you have some time series data or something like that, that's what a wide column database would be for. It does have that kind of flexibility that document-based databases have, where we don't necessarily have to have a schema, but sometimes we actually can have a schema with wide column databases. But while they are good for a lot of writes, it's better to use these databases when you don't need to read a lot and you don't need to update the database a lot. Like when you write something, you're not expecting to have to update it again, which would be the case with time series data and, some other types of scenarios as well. But among the databases we've talked about so far, these are definitely the most optimized for a massive amount of writing that we are going to be doing. Probably the most popular wide column database is Cassandra. It's open source. There's also Google Bigtable, which had some inspiration for Cassandra. But moving on to graph-based databases. These are all about relations, actually. When we talked about relational databases, we talked about foreign key constraints. We talked about having multiple tables and joining these tables together. Maybe we have a people table and we have a table for a bunch of cities with, information about those cities. And we want to join, people and cities together to get a person's home, their home address with their city information and all that. So we have like a middle table, which connects people to cities. And then with SQL, we would, do some join to join these tables together. But the point here is that we have relations between people and homes, homes and cities, and, people and cities. And as we get really, really large, like for example, if we're talking about like a social media site like Twitter or, Facebook or pretty much anything where it's all about the relations. Like, we have people, we have a bunch of users. Some people follow other users, right? Like this would be a follow. And maybe this person follows that same person back, or maybe they don't. Maybe this person only follows other people, but not this person. And maybe this person over here is followed by thousands and thousands of people, but they don't follow anybody, right? Like we have this relationship with social media sites, and this type of stuff can get very, very complicated. If you wanted to store all of this in SQL tables, and every time you wanted, for this person, who are all the people that they follow? And among all of the people they follow, what are like the secondary connections between these people, right? Like the way that Facebook will tell you friends of your friends, like do you have any mutual friends with somebody? Like these types of relations are hard to represent with SQL, and it can get really expensive if you want to have to do like joins on multiple tables, and you have to do that for like thousands and millions of records in a table. It's better to represent this type of problem, a social media site where we have follows and followers and things like that, with a graph, because graphs are really the natural structure. I'm talking about these types of directed graphs, and that's what graph DBs do, at least at a high level. So, this node would represent a person, and the edge from the graph would represent some type of relationship between these two people. In our case, this is follows, but we could have a lot more stuff and it could get a lot more complicated. That's kind of what graph DBs do. They actually build on top of SQL in some ways. Like they definitely keep the relational part. So I guess this isn't entirely a non-relational database, but we're just focusing on the high level. So you kind of get the idea of when you would use this rather than use like a key value store. So now I want to get back to the motivation for NoSQL databases. And as I kind of said at the beginning, the biggest thing is all about the scalability. NoSQL databases can generally scale a lot better than SQL databases. And it's all about the restrictions we put on SQL databases, on relational databases, especially the ACID properties, right? Like we have tables and we have a lot of stuff to do. We have to make sure transactions are atomic, that transactions are isolated, that they behave as if they were performed serially, and that data is going to stay consistent. When we say consistent, we mean that all the constraints, the foreign key constraints, the non-null constraints, the unique column value constraints, all those are going to be enforced. The problem with this is if we have a single database and it's really, really big and it's, handling a lot of requests, like thousands of requests per second, and we want to scale this database up, the easiest way to scale a SQL database is actually vertically, just getting more resources for that single database. If we try to scale horizontally, which we know horizontally is more unlimited, like horizontally is better if it's possible because it's much more powerful, but it's really hard to scale horizontally with relational databases because of the things that we talked about with ACID, properties with isolation. If we take this database and split it into, let's say, 2 databases to keep things simple, that doesn't mean we actually replicated the database. I'm talking about putting half the data in one portion and half the data here. So we would have 2 nodes, 2 different computers running half of the database each, right? So then maybe half the requests go to this database, half the requests go here. But how do we know how to route a request to the correct database? Like what if, one request needs data from this database, but it was routed to this one? Well, that's definitely a problem, and we won't go super in depth into it just yet, but there's actually a lot more problems with SQL databases. We need to sometimes do joins. What if our request was routed to this node and we're reading some data, and then we try to join some of this data with some of this data, and we try to enforce the foreign key constraints, the non-null constraints, the unique constraints, and all that stuff, especially the foreign key constraint, because we'd have to probably reference both of these databases. And to keep things consistent is going to be really, really hard because of all the stuff that we get, because of all the good stuff we get with SQL databases. This problem of horizontally scaling becomes really, really hard. And NoSQL databases actually do not follow these principles generally. I mean, many times they will have atomic transactions, but they do not guarantee the consistency. Well, they don't even have like those constraints, the foreign key constraints and all that. And they don't necessarily perform transactions in isolation. Generally, though, they are durable. Of course, not the memory databases like Redis and all that, but document databases and most databases are durable, but we don't get everything. And that's the point. NoSQL databases like document databases sacrifice ACID so that they can scale. So because when we split data, we can put half the data here and half the data here. We don't have any foreign key constraints to worry about, and we're probably not going to be doing joins between, half of our data here and half the data here. We're not going to be doing that. So this allows us to actually split data into multiple nodes and horizontally scale the data. This is the major benefit of NoSQL. Now, NoSQL databases also have kind of their own acronym. I don't think it's great. I don't think it's as good as ACID. It's definitely not as popular or as important in my opinion, but there is, a bit of knowledge that we can gain from base. And you can learn more about this if you'd like, but I'm just going to boil this down to eventual consistency because that's really what the entire acronym is about. I think it's a pretty poor acronym. And you know that because it's not even a full acronym. They kind of cheat and make this into 2 characters, even though eventual consistency is for the E. We don't have like an extra C over here, but whatever, let's kind of skip past that. But now let's talk about eventual consistency. We know that NoSQL databases can scale better because we can take data from one node of the database and split it into 2 nodes. But with NoSQL databases, we can also replicate nodes. Like we can have a node here. This is our database. And then we can create a replica of that node, which is basically a copy. So we have 2 copies of the same data. So how do we handle reads and writes? Well, if we write data to this database, then don't we have to write that same data to the second database? Or these 2 replicas may become inconsistent. When we say this word consistent now, we actually mean something different, slightly different than the ACID acronym. When we talked about consistency then, we were talking about the consistency of the data, that the data would follow the constraints that we specified, like the foreign key constraints and all that. But when we talk about consistency here with replicas, we're talking about, is the data going to be, in sync? Like if we write some data here, is it going to be consistent with the replica over here? Or are they going to be inconsistent? Maybe the value that we just wrote to this replica is not on this one. So when a user reads from this replica, they get the up-to-date value. But if a user reads from this replica, they do not get the up-to-date value. That's kind of a problem. And generally generally, one of the nodes of our database is considered the leader and the other one is considered the follower. So in this case, what we would actually do is every time we write, we're only going to write to the leader database. We would never write to the follower database because the leader is going to be responsible for all of the followers being written the same data. So eventually this leader will make sure that this data also gets written to this follower, but also any other followers that we may also have. In this case, we just have one, but we could have multiple followers, but we're only going to have this one leader over here. And NoSQL databases and this acronym BASE is all about eventual consistency. We sacrifice the fact that some people for a small portion of time will see out of date data. It's just like a cache, sort of like a stale cache, but this replica will have stale data. And for a short amount of time, users might be reading this value and they may see a non-up-to-date value. Like if you were looking at a tweet on Twitter and you saw a follower count for somebody that's smaller than what it really is, it wouldn't really be a big deal in most cases. That's why NoSQL databases are powerful. Yes, in some cases we may get a stale value for a short amount of time, but eventually this replica will have the most up-to-date value and then we are good to go. There's no guarantee on how long that time may take. It could take a long time, but usually it's not. It's pretty reasonable, on the order of milliseconds or seconds. Now, technically, we could have database replicas with SQL databases as well. It's just that this kind of scaling, this replication and, partitioning of data, like taking a database and breaking it into smaller pieces, or in this case, taking a database and creating a copy of it to handle additional scale, because that's kind of why we're doing this, right? Even though we can only write data to a single, node of our data, only a single replica, when we read, we are able to read from multiple replicas, even if we're getting some possibly stale data. We are able to handle a higher amount of read capacity, even if we have the same amount of write capacity, because generally reads are what people are going to be doing. When you open up Twitter, you're probably going to be scrolling through your timeline. You're probably not going to be writing 100 tweets. But these are the trade-offs that we make with NoSQL. We can sacrifice data consistency for eventual consistency and be able to handle more reads. And we can also partition data. You can actually partition data with SQL databases. We'll sort of talk about it. It's sharding. It's just that NoSQL databases typically provide this by default. And if you do this with SQL databases, you actually split up a database into smaller pieces. It's very, very complicated to manage that with a SQL database. Because of all the constraints that we have, it can get really, really complicated, which is why it's a lot less common with SQL databases and why, document databases and key value stores and all that were introduced.